Greetings of the day. Myself Yogeswararao, and my paper title is an improved content-based image retrieval system for tomato leaf disease classification uh, under the esteemed guidance of Dr. R. Malmathanraj, Assistant Professor, and Dr. P. Palanisamy, Professor, National Institute of Technology, Tiruchirappalli. Like the yield and quality of the agriculture products primarily depends upon the uh, plant leaf diseases. Like mm, mainly the people will identifying the plant leaf diseases. It's very difficult process to identifying that. So nowadays the machine learning approaches has came to picture to solve this problem. In this topic, like we implemented a content-based image retrieval system to identifying the tomato leaf diseases classification. Like the main objective is the novel content-based image retrieval system is developed to classifying the tomato leaf diseases. It uses like the contents are like color, shape, and the texture features of the particular tomato leaf, and to classify that based on the data set tomato leaf diseases. It's concerned to color features used in the proposed model. The HSV color histogram is used to extract the color features, and to concern the shape, Fourier descriptors are used in this proposed paper, and as well as concerned to the texture features, we used like the complete local binary pattern is used, and after getting the individual features of color, shape, and texture, we all combinedly fused and we form a single vector is called a feature vector, to nothing but to concatenate all the features of the color, shape, and texture. And after that we used a multi-class supervised learning as a classifier, and we use different kernels like linear kernel, RBF, like Gaussian kernel, polynomial kernel, by using the hyperparameter optimization, and as well as we used the cross validation, fold cross validation. In this concept we used 5-fold cross validation, and after that we are getting around 97.3% of the disease classification recognition rates. And the main concept is like the classification. We used color, shape, and structure features from the images, and to train the supervised learning model with multi-class SVM algorithm to classify and then identifying the diseases. As far as performance metrics are concerned, in this paper we calculated like performances like accuracy, precision, and recur, and of the individual each diseases, and the proposed automated disease identification system, mainly it will help to farmers by saving the plant from the leaf diseases, and as well as generally the identification of leaf diseases. Actually the human will identify individually. It's like a time consuming process, and it requires more skilled manpower to identify the individual plant and their leaves, but actually it requires more uh, uh, time to identify, and as well as it requires more skilled manpower also. But if you neglect the primary stages of identifying the leaf diseases, the entire yield will the entire form of the entire yield will damage. This is the main drawback. So by using this automatic identification system, we will save the plant and energy, mind, money, and as well as the resources. Okay, and we can identify the plant from the initial stage to take an action. And these are the we in this concept we considered four, along with the healthy total five leaf diseases we are tomato leaf diseases we considered in this topic. And in the pre-processing step we used resizing like to maintain in the uniformity of the entire database. So we used 533, I mean 800 by 533 pixels of the size we maintain. And in this concept we used the segmentation using the k-means segmentation of the k value 2, where the k value 2 indicates that the uh, background and the original the object, the reason of interest what we are choosing. So this is the shown from the image we can show this is the original image, and this is the segmented images of the k value 2. One is the background and second one is the object. Why we are using this concept is we can get the only the diseased parts of the particular objective of the image only we can consider from this. So we use this is the pre-processing steps. Coming to the feature extraction, generally we use like LBP, local binary patterns, but there are some limitations in the LBP to find the structural features. The main thing is the histogram, the long histogram, so that it will slow down the recognition rates of the data sets if it is considered for the large scale databases. The next one is it sometimes it may fail to miss the local structure of the original images, and also they are sensitive to noise, and they have like a small spatial upper areas also become. So in this concept, in this paper we used like a the variant of LBP is nothing but the complete local binary patterns used in this CLBP, like complete local binary pattern. We calculated like two components we will find. One is the sign component and next one is the magnitude component. The magnitude of the component is calculated by the difference between the center pixel and the neighboring pixels, and the difference is compared with the global mean and converted into an 8-bit value. Here is the SP and MP are represented the sign of the sign component and as well as the magnitude component, where WP is the neighboring pixel weight and WC is the center pixel weight of the sign. We will get the sign component and as well as the difference between the neighboring pixel and the center pixel magnitude we will get. And the CLBP components, like if the neighboring pixel value is greater than or equal to the center pixel, then the weight will come at the sign will come as a 1. If the neighboring pixel value is less than the center pixel value weight, then the sign will come at as a 0. Based on that we will get the sign component of the complete local binary pattern. And here the main thing is we will consider, as in the LBP we didn't have this feature like the magnitude component. Now we are calculating this magnitude component of the, based on the magnitude, like the difference between the center pixel and the neighboring pixel, if it is greater than or equal to the certain value C threshold, where C is nothing but uh, the mean value of the entire image what we are considering. If it is the magnitude value of the difference of center pixel and the neighboring pixel is greater than or equal to the threshold value, mean threshold of the particular image, then it will give it as a 1, and if it is less than the threshold value then it will give it as a 0. Based on this concept we will get the magnitude component of the complete local binary pattern. So after getting the color, shape and the structure features, from the color we will get the HSV color space and the proposed, and as well as the shape features we will get from the Fourier descriptor, and the texture features we will get it from the complete local binary pattern. We will form we will concatenate linearly one by one of the each feature, and we will form a vector, that linear vector as a single vector from the each particular leaf, diseased leaf, and from the entire database we will form a each like a vector wise we will concatenate all the features in that particular image. And after that we will create a feature bank of entire data set. This is nothing but feature combination. In the disease classification, we use like a multi-class support vector mission as a classifier to find the boundary that it separates from the different classes and maximizes the margin between the each individual class. And the evaluation matrices as concerned to, we use like a confusion matrix as a, and precision, recall and F score values are computed from the confusion matrices. And as come to the result part, like the classification we compared with the different architectures, like only RGB compo histogram values and HSV histogram value, Fourier descriptor, gray level LBP, hue value of considered with LBP, and gray level of complete local binary pattern and hue values of complete local binary pattern, and the hybrid models like RGB histogram of the color and Fourier descriptor of the shape and gray level LBP, and as well as HSV histogram, Fourier descriptor and hue of LBP, and RGB, FD, I mean Fourier descriptor and gray level. Like that we will have different combinations of the feature sets we compared along with the different models. Out of all we will get the combination of hue HSV model and Fourier descriptor and hue CLBP is getting the best value. I think it's not visible here. On the next slides we will see that it's around 97.3 we will getting. And from the confusion matrices concern, we will use the almost 70% of the training and 30% of the test set we use. We will normalizing that. We use total 5 diseases including the healthy. So we will get the individual representations of the predicted values and the true values. Based on that we will get the accuracy values, recognition rates of that, and as well as we will get the precision, recall, F score, and how many vectors, support vectors we used in that from the total 5 different types of diseases. And we will get the averaging of all individual like precision, recall, F score values also. And this is the k-fold cross validation. In the SVM we used 5 k-fold values, I mean 5-fold validation. Every fold we will get the accuracy values, and the mean is around 97.3% of it. I mean k values also we will get k-fold validation. And this is for different accuracy plots for different leaf diseases, like different combination of the feature sets like HSV, Fourier descriptor, hue CLBP and gray level CLBP, Fourier descriptor and RGB, different combinations of hybrid combination of the feature sets like color, shape and texture. Based on that we will calculate the accuracy values of different leaf diseases. Like here we will calculate the spectorial spot and healthy leaf and bacterial spot and late bright and tomato mosaic. Different we will these curves are like it's a combination of different features and as well as different leaves. And from the conclusion we can say that like the proposed content-based image retrieval system is practically implemented for agriculture users. 4 types of tomato leaf diseases are taken into account, and the k-means clustering, like based on the segmentation we use that k-means clustering and bilateral filterings are performed in segmenting the region of interest and remove the noise of the background, and we can get the only for particular region of interest, nothing but particular disease leaf, only the leaf parts only we will consider. And the individual performance of color, shape, texture features are calculated, and we analyze it to form a vector to get the results, and the training and classification model is implemented using the support vector mission. The maximum mean classification accuracy is around 97.3% of time by the combination of out of all the HSV histogram features and Fourier descriptor and as well as the hue CLBP features. Like HSV color histogram, it's giving the actual color features of the image. And anyway, that CLVP we consider as a both sign and magnitude component by because of this combination. Since these combinations of HSV color and Fourier descriptor of the shape and CLBP of the features like the structure features, but the particular combination we got the 97.3% of the accuracy. And the databases and all we got from the plant leaf village databases. And in future, like no, like actually this model is very much helpful for the farmers to save the plant, save the plant, and as well as to improve the quality and as well as quantity of that particular products. And it's like a normal procedure is like a time consuming, but here we can get best solutions from the less time, and we can identify each plant and each leaf also. So like in future this work can be extended in a, like a creating a mobile application to scan the leaf and identifying the classification of diseases. There is one possibility. And then the actually in the present work we used only 4 type of, including healthy, total 5 type of leaf diseases only we considered. And in future we may increase the different types of leaf diseases also. And as well as in this we use some machine learning technique. In future we can implement it like a deep learning algorithm instead of machine learning. In the deep learning, the training and as well as testing all instead of in the machine learning and all we manually select giving the features like color, shape, texture and like that. But in deep learning it's automatic learning process to get the better results. We can, by replacing the deep learning models we can get the, and these are the references what we used in this paper. Thank you.